Hello, welcome back to Math 332 Linear Algebra, and welcome back to the second part of the presentation on sections 1.8 and 8.1, which involve a very important concept in linear algebra, namely the concept of linear transformations and matrix transformations. So in the previous video, we have seen that for transformations that takes an element in Euclidean space Rn and map it to another Euclidean space Rm, in that case, the concept of matrix transformation and linear transformations is actually equivalent. And we have also seen the significance of it. And in this second video, we are going to look at some of the example that utilizes that concept. And in particular, we are going to find a standard matrix that can represent a geometrical transformations such as rotations, reflections, and all that. And we are again going to see how we're going to exploit the property that we learned in the first video, where we know how to compute the standard matrix for the transformations in order to describe this kind of geometrical transformations. And this is going to be pretty fun. And so I hope you enjoy it, and let's get right to it. All right, let's begin by looking at the objective for this section. So at the end of this video, you should know how to compute the standard matrix for all type of matrix transformation, in particular some of the geometrical transformations, which we're going to talk about in these videos. Okay, so before we do that, let's do a very quick review on the very important concept that we have from the previous video. That is the every linear transformation that is from Rn to Rm is actually a matrix transformations. And in the proof, we actually know how to construct that particular matrix, and that matrix is called the standard matrix that represent that linear transformations. The other direction is easier. That is, if you have a matrix transformations, then that particular matrix transformation is definitely linear. That's not a big problem. That's basically just a property of matrix multiplications. So let me give you this particular example. So suppose you have a linear transformation that is taking an element that is in R3 to R2, for example. So let's say this is linear. And if we know that's T100, that's the E1 that is from this domain. So if we know this T100 is, let's say, is 25, and let's say we know T010, that's your E2, let's say it's 15. And let's say you have T001, and let's say this is -14, then we know that this linear transformation is a matrix transformations with the standard matrix, which can be written as TE1, okay? And then you can write it as TE2, that's right here, it's TE2 and TE3. And so the standard matrix that represent this matrix transformation is 2, 5, 1, 5, -14. So everything that is in this linear transformations, T of x, okay, so this is going to be, let's say, our x, y, z. This is going to be 2, 5, 1, 5, -14, okay, x, y, z. And as mentioned in the previous video, this is a very powerful result in the sense that we only know the image, okay? We only know the image for this particular input. We only know this image for this particular input. We only know the image for this particular input. Once you know these three, so only knowing these three informations and T being linear, we now know everything about that map. So now we will be able to figure out what happens to T of x for every single possible x that is in R3 that you can think of. So that is very powerful result. And this is another example that we have seen last time. So this is a mapping from R2 to R2. So if we know TE1, in this case is 10, TE2, in this case is 0, 1, and then you will know everything about that linear transformations. Okay, so now we are going to look at this particular example right here. So right now, we are being told that we have a transformations which is linear, that takes an element that is in R2 and map it to another element that is also in R2. But now we are given T12 is 10 and T2 -1 is 0, 1. So the question is, since this is linear, we should be able to write this as a matrix transformations. And what should that matrix be, right? So if you said this is going to be like 1, 2, 2, -1, or if you say this is at 1, 0, 0, 1, then this is not true. This is nonsense. Okay, so remember, same thing as before. We still need to have T10. Okay, so we don't have that information here. So we have a 1, 0 here, but that is not T10. Okay, so we need to know what is T10, and we need to know T01. So what are those? Because again, if we know this too, we will know everything about that map. So the only problem is we are not given T10 and we are not given T01. Instead, the information that we have is T12 and T2 -1. So how do we deal with this? Okay, so remember, we still need to have this information that we don't really have. So the thing is, we would want to force, okay, we will want to find TE1. So so how do we do that? So we want to be able to write E1, okay, as a linear combination of these two informations that we have. So the key idea here is we want to write the E1 as a linear combination. Remember the terminologies that we mentioned before. So you want to write E1 as a linear combinations of these two vector 1, 2, and 2, -1. Why do we want 1, 2, and 2, -1? 1, 2, and 2, -1 is this right here. Which we know the image of. Okay, we know the image of 1, 2 under the map T, and we also know the image of this 2, -1 under the mapping T. So we know the image. The image is 1, 0 and 0, 1. So now we want to write 1, 0 as alpha 1 of this and beta 1 of this. And we also want to do the same thing for 0, 1. That's our E2. We want to write as alpha 2 of this and beta 2 of this. Now, you might ask, why do we want to do that? Because suppose we can find these two numbers, and then we can find these two numbers, then TE1, because T is linear, and we're using the additive and homogeneity property, you can see that TE1 can be expressed as this, okay, which we know T12 is actually 1, 0. And we know T2 -1 is actually this. So in fact, if we can find this number alpha 1 and beta 1, if we can find alpha 1 and beta 1, we know T10 is exactly alpha 1 and beta 1 because of this. Okay, so same thing, if you know how to find alpha 2 and beta 2, then because of the additive and homogeneity property, this is what we get. And in fact, TE2 will be known and it will be the alpha 2 and beta 2 that we get it from here. So the whole question now to construct this matrix A reduces to how do you solve this linear system and how do you solve this linear system, okay? So the things that we want to do is we want to solve this first linear system and the second linear system. So we want to solve this linear system. So solving linear equations is what we know how to do in the very, very beginning of the semesters. So just remember that solving this particular linear system is equivalent, okay, to solving this system, and solving this linear system is equivalent to solving the system. And this is just a 2x2 system. You can do row reductions or even like basic substitutions. You'll be able to find that this alpha 1 and beta 1 is this, and alpha 2 and beta 2 is this. There are many different ways you can solve for alpha 1 and beta 1 and alpha 2 and beta 2. So you can verify that this is your solutions. And if you don't get this, you should definitely try to row reduce or do substitutions to get this. So immediately we now know that T10 is this and T01 is this. So we have the standard matrix, which is given by this. So now we know everything about that map. So again, we now know everything about that map. Anything X, Y that you can think of, I can just multiply it with the standard matrix. So the standard matrix is right here. The standard matrix is right here. Then I will know every image of that linear transformations. Okay, so that is pretty neat, and this is one of the applications we can use in order to write down the standard matrix that represent that linear transformations. So remember, we still have to go back to this particular constructions. Just remember, we still need to know TE1 and TE2. And if you are not given TE1 and TE2, you have to find ways based on the information is given to try to construct TE1 and TE2. And this is one particular example that show you how to do that. Okay, and let's look at another example here. So now you are given that you have a transformations. These transformations take an element that is in R2 and map it to another element that is in R2. And how do you do that? So this transformation will rotate each point by 90 degrees counterclockwise around the origin. So you have, okay, a point right here. This is your xy. Or sometimes in linear algebra, we write like this, xy. Okay, so every point xy will be rotates 90 degrees. So it will be rotates 90 degrees. So this is going to be a 90 degrees. So 90 degrees is going to be something that's like this. And counterclockwise about the origins. So this is your origins. This is your x. This is your y. So xy will be rotated, okay, counterclockwise 90 degrees. Okay, so this xy here will now be mapped to here. So this is going to be a 90 degrees. So as you can see, if this is your x, okay, so that's the x, that's the y. So if you rotate 90 degrees counterclockwise, okay, counterclockwise around the origins, okay, so oops, this thing is gone. So you will see that the coordinate will change accordingly. So the coordinate will change in the way that this point right here will be our, so if you have x, y, so this point right here will now change to the new coordinates here will be minus y, x. Okay, all right, so if you have a rotation 90 degrees counterclockwise about the origins, and this particular mapping will map a point xy to the point minus yx. Okay, and then you will see that you will want to show that this particular transformations is actually linear. So how do we do that? So as I said, for a point xy, okay, under this mapping will be mapped to negative yx. So negative yx can be written as x of 0, 1 plus y of negative 1, 0. So again, you can write this as this. Okay, so now you can see r of xy is a matrix multiply x of y. So now you can see that this r of xy is actually a matrix transformations. So this is a matrix transformations. This is the standard matrix, and that's the matrix transformations. And now you can see that because matrix transformation is linear transformations, so now we know that this particular transformation is linear. So this question here basically asks you to show that if you have a transformations that is a rotations around the origins counterclockwise 90 degrees, how do you know that this transformation is linear? And the way we show that this transformation is linear is to show that this transformation is actually a matrix transformations. So matrix transformations is definitely linear. And so therefore, this rotation, this particular 90 degrees rotations transformations is actually a linear transformations. That's how we make use of matrix transformation is linear transformations. And using that, you will be able to show that this particular transformation R is linear. Okay, one more questions remained. How do you know if you have a point, the coordinates is xy, how do you know after the 90 degrees rotation counterclockwise around the origins will turn this coordinate xy to minus yx? Okay, how do you know that? Well, this is easy. So let's look at this coordinate. So if you have a point, coordinate is xy, then you would know that this part right here, this is going to be y unit, okay? And this part right here will going to be x unit. Okay, so let's look at this part right here. So let's look at this, okay, this length right here. So this is your x. So this is easy to see. So if you have this x after 90 degrees rotations, it will end up to be here. So now your x will be right here. So this is your x. Okay, so your y, which is right here, will be right here. So you can see like this L-shaped objects. This L-shaped objects has been rotated and to this. So now this is the x. Okay, so this is the x. So the length of this is x, and the length of this is y. So in terms of the length, this is length x. This is length y, but in terms of the coordinates, okay, so in terms of the coordinates, the x coordinates will now be this, but they are on the negative side, so this will give you minus y. And the y coordinates, where is the y coordinates? The y coordinates is given by this. The length is x, and that's your y coordinates, and that's what you get. So that is how you get the xy coordinates turn into minus yx if you have a rotations 90 degrees around counterclockwise around the origin. Okay. All right, so this concludes this particular discussion of this particular example. So now let's look at another example. So in this example, we are looking at rotations, but now we are not restricting ourselves by rotating it 90 degrees. So now we are rotating it with an arbitrary angle, theta, and we are still going to rotate it counterclockwise, and we are going to again rotate it about the origins, okay, center about the origin. And so now we've been told, okay, this can be shown, but we are not going to be bothered about that. But this can be shown that this kind of transformation is actually linear. So we've been given that this is linear. Your job is to find the standard matrix that represent that particular linear transformations. So as we know, what we need to do is to figure out the image of E1 under the rotation transformation and figure out the image of E2 under these rotation transformations. So we need to figure out what is this and what is this. All right, why don't you pause the video, take your time and work on that, and I will come back to you and show you what I have. All right, welcome back, and let me show you what I have. So remember, we need to figure out what is the image of E1 under this mapping and what is the image of E2 under this mapping. So if you look at E1, so remember E1 is right here. So this is a 1, 0. So after rotations 90 degrees counterclockwise, center around the origins, you will end up to be right here at this position. So we need to know the new coordinate. So the original coordinate is 1, 0. So now we need to figure out what's the new coordinate. So in order to find out the new coordinates, I need to know the length of this part right here. So that's obviously sine theta, and this length here is obviously cosine theta. So now the x coordinates for this new points right here. So this is your new r theta E1. So your new r theta E1. This new coordinate here, the x coordinate will be cosine theta, and the y coordinate will be sine theta. So that's what you have, cosine theta and sine theta. And your E2 is right here, or original E2 is right here. So your 0, 1, that's your E2. So your E2 after rotations, theta degrees counterclockwise, okay, center around the origins, you end up to this coordinate. So we need to figure out what is this coordinate. And so again, we need to know the length. So this one right here, the length right here is sine theta, that's the magnitude. And then the length right here is cosine theta. But in terms of its coordinates, you can obviously see that we are on the negative side of the coordinates x. So this one right here is negative sine theta. And the y is cosine theta. So that's the reason why we have this. And that is the reason why the standard matrix is given by this. So once we have the standard matrix, again, we will know everything about that transformations. So now for every x and y, it doesn't really matter what x and y is. So if you rotate theta degrees clockwise, counterclockwise, you will get to this new point, and that new point will be given by this product right here. Okay, so this is basically how we rotate a picture on your iPhone or whatever. You take a picture and you want to rotate, you want to flip it over, you want to rotate 90 degrees, 45 degrees, this and that. We can do that because this is just basically writing a program to ask the program to execute for every x, y coordinates. Let's move it to the new coordinate, which is given by this, and which is pretty easy. And let's look at another example right here. This is basically a type of application, type of things that we already have. So let's say you have apples, and then you perform that transformation by flipping it to here. And suppose this can be done by a linear transformations. And if that's the case, what is the standard matrix that represent that linear transformations? And you can kind of like just observe where this particular leaf of that particular apples will go. You'll see that this is actually a 90 degrees rotation clockwise. So this is a 90 degrees rotation clockwise, center around the origin. And because we already have the formula, right? Because we already have the formulas, and this is clockwise, so this is minus 90 degrees. So we are going to put all the informations that we have just now, and we already know how to do that with the general theta. So now your theta is 90 degrees minus 90 degrees, because remember the convention is that if you go right here, this angle is positive, but if you go right here, this angle is negative. So we put this thing into, this is a minus 90 degrees, we put this thing into this matrix, and you will see that the standard matrix that represented is this right here. So this is like one way we can utilize this kind of standard matrix idea, the procedures, in order to be able to properly describe what is that transformations, what is that matrix A. Okay, so now we wanted to do all this thing in 3 dimensions. We can still do exactly the same thing in 3 dimensions. So I'm going to give you this question. So you have, this is a x, this is a y, this is a z, and I want you to find the standard matrix which represent rotations about the x-axis. So first one is rotation about the x-axis with the angle theta. If they didn't really mention the orientation of the theta, we'll always assume the positive, which is the counterclockwise directions. So I want you to write down a standard matrix to represent that. We can show that this kind of rotations and all that is a linear transformation. So we want you to find a standard matrix that represents that rotations. Okay, so what is this standard matrix? So again, you need to know TE1, okay, TE2, and TE3. Sorry, this is R, and R. And your E1, E2, and E3, obviously, in this case, is your 1, 0, 0, your 0, 1, 0, and your 0, 0, 1. We need to be able to find that. If you know how to find that, then we will know what's the answer for that standard matrix. So let's do one more since we are right here. So let's do one more example. This time we are going to look for the standard matrix that represents the rotations, but this is about the y-axis through the angle theta, again counterclockwise, and you will want you to write down the standard matrix. So again, you need to know what's the R1, RE1, RE2, and RE3. All right, I'm going to suggest that we pause this video for a little bit, and so that we can give this problems full considerations. And once you think you have the answers, you can get right back to it. All right, see you very soon. All right, welcome back. And as I said, we need to know what is the transformations, TE1, TE2, TE3, or your RE1, RE2, RE3, doesn't really matter. So since this is the rotations on about the positive x directions, it's positive x direction, so your x, this is basically, you know, x direction. This is for people who are taking physics. This is your ijk vectors, basically. So this is your x direction. So this is a 1, 0, 0. So because the rotations is centered around this line, so you are rotating, okay, you're rotating about this axis, so this particular vector will not be affected. So we know that the image of 1, 0, 0 under this mapping, under this transformation, will still be 1, 0, 0. However, if you have a vector which is your j, so to speak, your ij and k, right? So this is your j. So your vector j, this is a vector j, which is 1, 0, 1, 0, now will be rotated, right? So it will be rotated, angle here is theta. So let's look at this picture right here. So let's look at this picture right here. So originally, you are right here. Yeah, this is your original positions, and your coordinates is 0, 1, 0. But after these transformations, rotating theta degrees counterclockwise, this is where you get. So this is your new positions. So I need to know the coordinates of these new positions. So obviously your x coordinates will be still 0 because we are looking at the plane. We are on the plane YZ. We are on this plane. So we are on this plane right now. So this is the plane that we are on. This is the plane that we are on. And if you're on this particular plane, your YZ plane, obviously your X will be 0. So that's explain why you have this. And then now you are not in the 3 dimension anymore. You are just basically on this plane. So now you're in 2 dimensions. So just concentrate on here. You will see that this coordinates, this length right here is sine theta. That is your Z positions. So you can see this is your Z positions. That explains why you have a sine theta right here. And then you will see that the y position have length cosine theta. So that's why your y position here have a cosine theta. And they are all on the positive z direction and the positive y directions. So in terms of the sign, this is positive cosine theta and this is positive sine theta. And that gives you 0 cosine theta and sine theta. So you can see this is your TE2. Okay, this is your TE1. All right. Okay, so finally, let's look at what happens to your vector E3. This is your IJK, that's your K positions. So this part here will be rotated right there, right? So let's concentrate on this picture right here. So originally your 0, 0, 1 is right here, but then after that rotation, you will get to here. That's the angle theta. So again, in terms of length, this is cosine theta. In terms of length, this is sine theta. And against your, we are on the planes, YZ plane. So we are on YZ planes. Your X is going to be 0. But again, let's look at the Y position, right? So the Y positions is going to be right here. So your coordinates has a negative Y position. In terms of length, the length is sine theta, but you're on the negative direction. So you have a negative sine theta. And your z has length cosine theta, but you are on the positive z direction. So this is cosine theta, positive cosine theta, and this is where your TE3 will go. So your TE3 will go to 0, negative sine theta and cosine theta. Okay, so the next problem is similar. If you know how to do this, you will know how to do the other one. So we have our TE1 right here, TE2 right here, and TE3 right here. Why is that the case? Again, let's look at this part right here. So now your rotation is just about the y-axis. So obviously your y will not move. This explains this. Okay, your TE2 will still be TE2. But let's look at what happens if you are concentrating on the z and your x plane. So your xz plane. So you look at the xz plane. Okay, so let's look at what happens to this particular vectors. Your E1, so your T1, 0, 0. So let's look at this picture right here. So if you are rotating it counterclockwise, 90 degrees, sorry, theta degrees counterclockwise, so you'll see that position here, this one right here, right, will go down, right? It will go down and it will go down like this. So just again, concentrate on the Z and the X directions, the Z and the X directions. Okay, you will see that this part right here will go down. So it will go down right here. So it will go down like that. So in terms of the length, okay, so in terms of length, this one here is cosine theta. This one here is sine theta. But your sine theta is going to be on the negative side of Z. So you will see that your x, y, z here in terms of coordinate, x will be cosine theta, still on the positive x directions, still on the positive x direction. This is a positive x direction according to the picture. According to the picture, we draw it like this, okay? So it's draw it a little bit different. So this is our z, this is our x. So this is our positive z direction, this is our positive x directions. So now, in terms of the x, we have the positive x cosine theta, y is 0. And in terms of the z, this is sine theta in terms of magnitude, but we have a negative sign because we are on the negative side of the z. So that explained why you have TE1 looks like this. Cosine theta, 0, and negative sine theta. This is easy to see. This is no problem. And then finally, let's look at what happens to T001. So your 001 is right here. So this one will get rotated right here, right? So let's concentrate and look at this picture. So the magnitude, if you rotate theta degrees away from the z counterclockwise, so the magnitude of this is cosine theta, the magnitude of this is sine theta. They both are on the positive z direction and positive x direction, so this is easier. So in terms of its x, position x, where is it? X position is sine theta, y position is 0. And what is the z position? Z position is cosine theta, so that's the reason why you have that. So this is your TE1, this is a TE2, and this is a TE3, and this is the standard matrix that represent these kind of transformations. Everything's still the same, just that we are in R3. And that's how you get all these standard matrix. All right, this concludes our two parts discussions on a very important concept in linear algebra, namely the concept of linear transformations and matrix transformations. So I hope that you learned something today, and I will see you in the future. All right, goodbye.